Thank you. Thanks to Zheng Zhong's talk, he talked about this great new framework. And if you still have questions from Zheng Zhong's talk, don't worry, because I'm essentially going to re-give his talk, but using my own words. Actually, what happened is like Zheng Zhong, a couple of years ago, Zheng Zhong came to CMU and gave a talk on his paper. And then he talked about this gate-by-gate obfuscation approach to constructing I/O. And then after listening to the talk, we were working on some paper at that time called non-interactive anonymous router, and we needed a quasi-linear I/O. And after listening to Zheng Zhong's talk, I told my students, oh no, Zheng Zhong scooped our paper. And then my students went and looked at his paper, and then they came back and reassured me, our result has not been scooped. And then I said, okay, why don't we rewrite his paper in a way that can get us the result that we want. Okay, so this is this talk. Everyone has to have a Swiss Army knife slide, otherwise it's not an I/O talk. From the candidate I/O to the I/O from well-founded assumptions, right? There have been many attempts that try to show the feasibility of constructing provably secure I/O from better and better assumptions, but very few have looked at how to construct efficient I/O, and this is what we are going to focus on today. So let me also talk about some related work. There's like two lines of literature. Like one focuses on provable security, and other constructions in this literature, like they have polynomial blowup. And in fact, all these papers don't even bother to quantify this polynomial, so we don't know how large this polynomial is. Zheng Zhong talked about this non-falsifiability barrier, which I call input length barrier. So that there's essentially a conjecture that seems to suggest any provably secure I/O, the complexity has to be at least polynomial in the input length. I'll explain that a little bit more later. But there's also another line of work, and they've focused on efficiency, like they want to make I/O practical. But the constructions, they rely on VPP obfuscation, and as we know, VPP obfuscation is impossible. So these schemes are heuristic, and they don't have provable security. And in this talk, I want to show you how to get the best of both worlds. We want both provable security, but we also want to achieve quasi-linear efficiency. Okay, so actually, we are going to construct something that's slightly weaker than normal I/O. I use this EF I/O to denote it. It's like we are going to construct I/O for two programs that have succinct EF proofs of equivalence. I'll elaborate on that a little bit later. So this EF part is also called propositional proof, right? So we are going to make use of EF proofs of equivalence. And before I talk about how to get it, let me just show you the theorem statement. So we need FHE, one-way function, and I/O for polylog size circuits. And given these, we can construct a quasi-linear EF I/O. And the efficiency is proportional to, this is the size of the circuit, and this is the size of the EF proof. Okay, so this is the theorem statement. If the FHE has polynomial security, we get an I/O with polynomial security. If the FHE has sub-exponential security, we get an I/O with sub-exponential security. The other primitives we need, this also needs to be sub-exponential secure. Okay, so that's the theorem statement. Obviously, this EF proof is going to play an important role in this talk. I know Zheng Zhong kind of already talked about the motivation, but let me just say it again in my own words, right? So normal I/O security is if you have two circuits that are functionally equivalent, then their obfuscated versions are computationally indistinguishable. And I mentioned there's this input length barrier, which Zheng Zhong called non-falsifiable barrier. This is just a conjecture. And the intuition is, it seems like the reduction has to decide whether these two circuits are equivalent or not, and it can only break the underlying assumption if they're equivalent. But in general, we don't know any better way to decide if they're equivalent other than just enumerating all possible inputs. And so it seems like the reduction has to run in time exponential in the input size, or in other words, maybe the number of hybrids in the security proof will be exponential in the input size, and this means the underlying security parameter of the underlying primitives has to be polynomial in the input length. Of course, this is just a conjecture, right? We don't know if how to actually prove something like this. But there seems to be some barrier to make I/O more efficient. And Zhenzhong and Abhishek, they have this blueprint. They are going to just let the reduction know the proof of equivalence. And formulated in another way, we are going to relax I/O security. Instead of requiring indistinguishability for any two functional equivalent programs, we only require indistinguishability if these two programs have a succinct proof of equivalence. Okay, so what's powerful about this framework is because it seems like for most of the applications of I/O we know, this EF proof of equivalence is like, it's sufficient to express the papers we have written in the past. And I can also show you some examples later. Okay. So how do you make use of the fact that we have a short proof of equivalence to make the I/O more efficient? In Abhishek and Zhenzhong's blueprint, this is the sequence of the locally equivalent circuits, right? So I want to take C and C prime, which have a short EF proof of equivalence, and I will introduce polynomially many hybrids. And in between each hybrid, like these two adjacent circuits, they are identical in structure except for like a small log size subcircuit. So I call this log n equivalence. So more specifically, these are two equivalent circuits. And this is the color part is where they differ in structure. But keep in mind that even though this color part differ in structure, they have to be functionally equivalent. And the whole circuits are functionally equivalent too.
Is it constant or log?
Log.
Mm-hmm. Log, okay.
So if you leave aside the length requirement, can you go between n two functional equivalent circuits, replacing log size blocks?
Sorry, I don't understand the question. Can you go?
So if you're happy about long proofs, can you prove equivalence between n two circuits which are functionally equivalent?
I think this comes down to this NP versus co-NP question.
No. I'm saying that the sequence may be very long.
Okay.
So yeah, so without the bounds on the length of the proof, so it could be exponential.
I mean, then you can always go to the minimal representation and back. No?
Can you?
But it has
Maybe you can enumerate over all possible inputs.
It has to be local. That's the issue. But never mind.
You can enumerate over all possible inputs. Maybe that's one way to.
It's like exponentially long extended Frege-able proof.
Each step corresponds to an enumeration.
So maybe the log in is
It can
okay.
be done this way.
Maybe log in is okay. Constant is probably not.
But if you do that, there will be a very large overhead on the side of the circuit. On the side of the
Okay.
Just as understand.
So because of this hybrid, it seems like it's sufficient to get I/O for log n equivalent circuits, and that's what we are going to focus on. Okay, so to implement this blueprint efficiently, we encounter two challenges. Challenge number one is like, how do you take two circuits and take their equivalence proof and just write down this hybrid? And then the challenge number two is like, once we have this hybrid, we need to construct I/O for log n equivalent circuits. How do we do that? And in both steps, you can lose some efficiency, and it's important to keep the efficiency loss small in both steps. In Abhishek and Zhenzhong's approach, for addressing the first challenge, right? So you have to do the padding of the circuit such that you can write down this hybrid, and they already incur quadratic overhead with this padding step. And then when they take this quadratic size circuit and compute an I/O for it, there's another quadratic blow up. So n squared becomes n to the fourth. So their scheme has to suffer from at least an n to the fourth overhead. And this is assuming you can have like a bark with ideal efficiency because their construction relies on bark. And it's actually not known how to construct bark with ideal efficiency yet. Okay, so in order to get it to quasi-linear, we have to overcome both of these efficiency challenges. So in our scheme, we proposed a new padding scheme. And essentially, we just have like polylog blowup during the padding step. And then when we construct the I/O, we also only have like polylog blowup. So we can keep the obfuscation time and evaluation time quasi-linear. Okay, so what I will do now is I will first give you like a 30,000 feet view of both steps, and then I'll dive into each step.
So by n, you mean literally the number of circuits, or you mean number of gates or number of gates plus original?
So sorry, for simplicity, I will just I will just assume the proof size is roughly the circuit size, so I can use a single n. But in fact, it's like n circuit plus n proof. Okay. So to solve the first challenge, essentially we are going to pad the circuit to some kind of universal circuit, because actually I forgot to mention, like this entire hybrid, they also have to have the same topology. So that's why, so at the very least, we have to pad it to some universal circuit so they all have the same topology. But the universal circuit part is not the interesting part. The interesting part is actually the bells and whistles part. And this is like, so we need to construct a universal circuit such that this hybrid is possible. And this part is the interesting part. Okay, I'll show you how to do it in a little bit. I mean, this just shows you how the universal circuit looks like. It doesn't actually show you the bells and whistles part. But I'll go into details later. This is just like a high-level view. And to solve challenge 2, we still use the gate-by-gate obfuscation approach of Abhishek and Zhenzhong. And when you try to obfuscate the circuit gate-by-gate, there's an important attack called the mix and match attack. Like the attacker can take values from 2 different evaluations and mix them together, and this can cause information to leak. So in order to prevent the mix and match attack, Zhenzhong and Abhishek's paper uses bark. So every time you have like an augmented circuit which corresponds to the every gate, augmented gate which corresponds to every original gate in the original circuit. And this augmented gate is going to check a bark proof of provenance, meaning if you have 2 input wires, let's say you have like 2 ciphertexts, each coming over an input wire, I have to check that these 2 ciphertexts are computed from the same computation and not 2 different evaluations. And this is where they need the bark. But the problem is like, to compute the bark takes linear time, because like you need to kind of compute some hash over all of the previous wires that it depends on. So every wire takes linear time, and you have, let's say, linear number of wires, so that is another quadratic factor. Okay. So if you can get quasi-linear I/O, like you can have some interesting applications. Like for instance, we also show how to construct multi-input functional encryption with quasi-linear efficiency, and how to get I/O for Turing machines with quasi-linear efficiency. I mean, this is also for unbounded input length. And in both cases, we have to assume short proofs of equivalence. Okay, so let's now dive into more technical details. I can show you how each step is done. So first, how do we solve this padding challenge? Okay. So I have 2 circuits, C1 and C2. And I know some equivalence proof. So I want you to think of, like, let's imagine we express this EF proof as a circuit. And this is what it looks like. The equivalence proof, like, the input wires are like the outputs. Like basically every wire in the C1, C2 part can be provided as input to the proof part of the circuit. And then the output of the proof part of the circuit is like, for every proof line you have in your EF proof, it will output a wire. And that wire is like, you can imagine it's an expression computing that the expression evaluated in the proof line. So you can imagine, like, for instance, initially, the expression P1 and P2, they are just true, like these are axioms. So this means implies. So to the left of the part is the premises, and to the right is the conclusion. This is like a proof line that doesn't need any premise. So now, for instance, if you have like some axiom that says if P1 and P2 is true, then P3 and P4 are true. Okay, so this, like, for instance, for the conclusion part of this proof line, you'll have wires that are output from the proof circuit corresponding to those proof lines. And finally, there has to be some expression that basically computes the expression out1 equal to out2, like the output of the circuit C1 on some input X and output of C2 on the same input X. So the last proof line has to assert that the outputs are equal of the two circuits.
What are the operations? I mean, so far,
Huh?
I mean, you're just putting variables P1, P2, P3, P4.
Yeah. I mean, I'm just trying to set it up to tell you how to think of this EF proof. So this is still just setting it up. I want you to think of EF proof as a circuit. This is how to think of EF proof of equivalence of two circuits. And so this is like how you normally formulate EF on paper. Basically, the system has like some axioms, and each proof line here has to like basically be aligned with one of these axioms. But it's possible to do variable substitution, right? But in fact, I don't want you to read into these axioms because what these say, it doesn't matter too much because you can replace the axioms with any set of constant size tautologies that are like complete. Okay, so in this talk, the way I want you to think of EF proof is like this. This is the most important. It's like if you have a proof line, if P3 is true, P4 is true, then P5 is true. So what does this mean in the circuit? That means there's a constant size subcircuit, and you can have these intermediate wires called Q1, Q2, Q3, and P1, P3, P4, P5 can all be computed from these intermediate wires. And this whole thing is constant size. And really, that's the way I want you to think of EF proof in this talk.
So how does the line P3, P4 implies P5 mean with respect to wire P3, P4, P5?
You just like you just need the conclusion of each proof line to be output from the proof circuit. This is like this. So basically, the conclusion of every proof line needs to be an output of this proof circuit, and you'll see how it is used later. Because like later on in the construction, like all of these have to be true, right? I mean, only if they are all true, then the proof holds. So you can imagine you're checking that all of these expressions are true, and you're outputting. You're just calling these output wires, so you can check if they're true or not.
So the wires P3, P4, P5 will be true if you input anything into queues.
I mean, basically, all of these wires have to always output one, no matter what the input is, and only then the proof holds.
I see.
Okay. Yeah, it's maybe in the beginning it's a little bit weird to think of it in this way, but essentially, all these, like when you write down a proof on paper, it's a bunch of proof lines, and every proof line has a conclusion, and all of these conclusions have to be tautologies. They have to be true. And then, like, I'm encoding it as a circuit, which is like a circuit that computes all these conclusions of all the proof lines. And those wires representing the conclusions have to be true, no matter what the input is.
So replacing everything in the middle by an extension variable, and every time you tell other gate.
Yeah, the extension is already implicit when you represent it as a circuit. Like, you know, in EF proof, the difference between Frege and extended Frege is extended lets you do this extension, and only when you allow this extension can you express it as a circuit. Otherwise, it's a formula. Like you can, the way to think about it is like in the circuit when you, like this is already doing variable renaming, right? I'm calling this Q, but Q can be, when you expand it out into a formula, Q can be a long formula. And only because of the extension rule can I express it as a circuit.
I guess I can totally see how circuits describe how different variables relate to each other. Like that seems to be pretty circuitish. I guess I just don't know how to view that a line says P3, P4 implies P5.
If this is a tautology, if P3 always outputs 1 and P4 always outputs 1, then it has to be the case that P5 always outputs 1. If this thing is an axiom, a tautology. So like checking the proof is just like, okay, if all these things evaluate to 1, then the proof holds.
I see.
Okay. So just to give you some more insights, like I can show you some example where of like these are the kind of proofs we write in crypto papers, and sometimes they don't have a short proof of equivalence. Like Brent gave a talk this morning. I guess he didn't use PRG as an example, but this is also from Brent's paper. Yeah, I decided to tell some jokes to entertain the audience. This is pretty late in the afternoon. All right, so this is like a typical kind of reduction you would do in this IO style proof. Like basically, you are going to check if like the PRG of some input is equal to some number R, then you do something special. Otherwise, you proceed normally. And then in these IO proofs, you are going to pick R such that it is not in the image of the PRG. And then you can say, because R is not in the image of the PRG, I can delete these lines. I can just do this. But you can see like these two programs don't have a short proof of equivalence unless like NP is equal to co-NP or something. So that's an example where it doesn't work. But fortunately, like even for something like this, there's a way to modify it slightly. Like this issue actually came up a lot in our paper when we were trying to like develop applications using this weaker form of I/O. Like if something like this happens, we would replace it with like we are going to let C be an encryption of 1. So if this is saying like if C is an encryption of 0, then do something special. Otherwise, proceed normally. But if the encryption scheme is perfectly correct, this thing can never hold if C is an encryption of 1. So you can also just delete these lines. But in Abhishek and Zheng Zhong's paper, they show like for natural encryption schemes like RAGAV and DDH, Algoma, they do have like a short EF proof of perfect correctness. Okay, so this is an example. So I can tell you how this padding is done and explain how to construct this hybrid. And the way the padding is done, this is very similar to Zheng Zhong's slide. Like, let's start with C1. I want to pad C1. So at this moment, like the construction doesn't know what C2 or the proof is, right? So the C1 is what I know. I will compute a universal circuit for C1. And the C2 part, I don't know what C2 is. This is just like a filler part. It's like all of these gates in this part always output 1. And then the proof, the construction also doesn't know. So this is just a placeholder for the proof, and every gate here constantly outputs 1. So that's the initial state. And I want to eventually, through like a sequence of hybrids, eventually get to a padded version of C2. The hybrid looks similar to what Zheng Zhong talked about. So first, like I'm going to grow the C2 part, then I'm going to grow the proof part, and then I will like, okay, I want to also mention, maybe I didn't mention that this triangle is like an entry, and that's important. It's like basically if the proof, these, remember like Rachel was asking like the output of this proof, right? These are the output wires, and they should always output 1. So like if they output 1, if these two programs are equivalent, then they should always output 1. And then you can see like the output is just computing C1, right? Okay, so I want to give you a flavor of what this looks like. I will not do it step by step. I'll just pick, I think this is the most difficult step. And I can show you how this step works. So what's happening in this step? I'm replacing the proof. Here it's just constantly 1. It's a fake proof. And here I'm replacing it with real proof. And to do this step, I actually need to still like do it. There's an inner hybrid. I'm going to replace it kind of gate by gate. So OK, so the way to think about it is like this triangle is just like the entry in the previous slide. And these are outputs from the proof part of the circuit. So like I guess let's assume like we have already replaced like all the other gates with the real version. And I've replaced A1 and A2 with the real version. So in this tiny little hybrid, I want to change this star gate from a 1 gate to a real gate. So I just want to make this tiny change. And basically, there's an axiom that says if A1 is true, A2 is true, then B is true. OK, so the problem is like when I make this tiny little change, like I want to draw a boundary such that a boundary that covers this star gate, such that the circle I draw that is like unaffected by this change. Like it's like the star is where I throw a coin into the water. It has some ripple. The ripple will propagate, but it will not propagate very far. It will like there's like some circle you can draw, and this is as far as it will propagate. So in this particular case, this is the subcircuit that are like structural, that are, what should I say, that are, the implementation of the subcircuit is different in the two hybrids, but the functionality is the same.
Sorry, you're saying the boundary has the property. The boundary you're looking for is such that like the two subcircuits inside the boundary are functionally equivalent. That's what
I want to contain the effect of this local change.
Because,
but I cannot just draw a circle here because apparently this gate has changed, right? But but this gate has changed. It will propagate its effect, like they're like ripple, but it's not going to propagate very far. So there's a circle I can draw that contains the effect of this local change, and this is like what's entailed in this kind of proof. So more specifically, actually, each gate here corresponds to a gate in the original circuit, and I call it a regular gate. And each line here, I'm abstracting away a lot of things. Each line here is actually a path through the routing network. It's not a wire. It's not a wire in the original circuit. And this is because, so the different circuit is just like this subcircuit, including all the gates on these paths. So just like the universal circuit part is not particularly interesting. It's more like the hybrid sequence part is more interesting. But just to show you how the universal circuit works, like I have a bunch of gates that are regular gates that correspond to original gates in the original circuit. And then like I have these two input circuits, C1 and C2. They may have arbitrary topology, and I have to make them the same topology. And what do I do to achieve that? I'm going to use like a routing network.
It's sort of a fact tree.
Huh?
It's a fact tree where
it's a what?
A fact tree. Never mind. So the routing is done from faraway places. It's done through the golden color.
It's just like for this particular gate, they are connected to these three gates. I mean, this is like, it's similar in spirit to Valiant's universal circuit. Actually, there may even be a way to just make Valiant work, but we did it this way because it's simpler, conceptually simpler. But I'm not going to get into the details of the universal circuit because I think that is not the interesting part. The interesting part is like you have to construct a universal circuit with these bells and whistles in mind. So you cannot just throw any universal circuit at it and claim it works. OK. So that's the first challenge. We solved the padding part. And then now we have to solve the second challenge, which is how do we construct an efficient I/O for log equivalent circuits. I think, how much time do I have? half an hour? Okay. So I think this is the part that Zhenzhong kind of skipped through. So a strawman idea is I will implement every gate in the original circuit using this augmented gate. And this augmented gate is going to take a ciphertext and a signature for each wire. So this gate has 2 input wires. So I'm going to check if the signatures are valid for these ciphertexts. And if they're indeed valid, I will decrypt the ciphertext, get the original value on those wires. And then I will compute the logic of the original gate to get the output. And then I will encrypt the output and compute a signature for the output wire. So the problem with this approach is this mix and match attack. Like, it doesn't prevent you from having 2 different evaluations using 2 different inputs and then mix them in the evaluation. And in order to prevent that, Zhenzhong and Abhishek's idea is to, so this H1 and H2 are, you can view them as a hash of all the wires this wire depends on. Okay, so I'm going to provide the ciphertext, the signature, but also the hash of all the wires that I depend on. And I'm going to give you, so H prime is the hash of, the hash that I didn't draw the output wire, but let's say the set of wires that the output wire depends on. Okay, so then I'm going to provide a proof that all these hashes are consistent. They correspond to the same evaluation. Like, you cannot substitute wire values from one evaluation to another. Okay. So in Abhishek and Zhenzhong's paper, the pi is a bark proof. And this is why it's expensive, because like the hash already depends on linear number of wires, and now you have to compute the bark for it, which is again linear per wire. So by the way, in order to make these hashes I/O friendly, you have to use somewhere statistically binding hashes. And then they use bark, but we want to get rid of the bark. So how do we get rid of the bark and make it efficient? We are just going to construct the, so we realize that all you need is some kind of prefix consistency proof. You don't need like such a strong bark for like arbitrary computation. Okay. So we are going to construct the an SSB hash with prefix consistency, and that's enough for the construction. So the way, and this is actually pretty simple to get if you look inside the SSB constructions in previous paper. I think this maybe is from Daniel's paper. Yes, it's HW15. Okay, so basically, I'm going to assume we just want it to be binding at one index. But in our paper, we actually need it to be binding at logarithmically many indices. But it's very easy to get from 1 to log n. So let's say I want to be binding at this index. And the way these SSB hashes are constructed is like, so there's this tree. It's very much like a Merkle hash tree. Like, you are going to you use some fully homomorphic encryption scheme, and there's a secret key, public key pair for each level. Like, for instance, this level has public key PK0, and then so the public key is like, I'm going to release the public key of all levels, and then at every level, I'm going to encrypt under the current level's public key of the next level's secret key, but I'm also going to encrypt the index that I want to select. Like here, the index I want to select is like 0, 1, 1. So I'm going to encrypt the next bit in the index. So if you give out these things as public key, what happens is like you can do a homomorphic evaluation. Like, essentially, to compute the hash, you will compute the ciphertext at all the leaves, and then you homomorphically evaluate until you get the ciphertext at the root, and that will be your hash. And the important thing is like this is kind of just like a Merkle hash tree. So for the purpose of the talk, you can just think of it as a Merkle hash tree. And if it's a Merkle hash tree, then prefix consistency proof is very simple. So here I have 2 inputs, and you can see they are prefix consistent, right? And these blue nodes are where the hashes are the same, and the gray nodes are where the hashes for these two inputs differ. So in order to give a prefix consistency proof, I'm just going to give the hash of these start nodes. And if there's only one star, I only have to give one hash because it's consistent among the two inputs. And if there are two stars, there are two different hash values. So I'm going to give two hashes. So these will become my prefix consistency proof. So this is like a pretty simple idea. But just this is not enough. You also have to show that you can incrementally compute all hashes and all prefix consistency proofs in linear time. And it turns out that can be done with like some careful algorithmic analysis.
Why is prefix consistency enough?
Yes, maybe I didn't explain that. Basically, we are evaluating the gates in a topological order. So if you think about it, like the dependency set of H prime is like going to be a superset of the dependency set of H1 and H2. So it's basically every wire is hashing all the wires I depend on. So of course the H prime corresponds to the output wire of this gate, right? So of course it depends on more wires because, for instance, it depends on the input wires of this gate. So that's why it's a prefix. Like I'm going to also order them using this topological order. So that's why all you need is prefix consistency. Okay, so I'm going to try to wrap up, and then, but before I do that, I guess like Zhenzhong mentioned Turing machine. So essentially with our result, we can improve his paper's result, and we can have like quasi-linear efficiency for the Turing machine evaluation time, but actually the obfuscated program size and obfuscation time is just like polylogarithmic. We have more things in the paper, like we have the detailed constructions and proofs. I didn't have time to talk about the details of the multi-input functional encryption or Turing machine construction.
Elaine, so what does the EF condition say about Turing machines?
Oh, that's a great question. So in my paper, I require the two Turing machines when you convert them to oblivious Turing machine. When you convert them to circuit using oblivious Turing machine transformation, the circuits have to have a EF proof. And not only so, you have to have an efficient RAM machine that generates this proof. So
it's not a proof on the Turing machine themselves, because that will be constant, right?
Yeah, I've been trying to ask people who understand PV proof whether I can relate that to PV proof on the Turing machines, but right now the answer, it's inconclusive because you can, in general, you can convert PV proofs to EF proofs, but there may be an efficiency loss. So I don't know how to quantify that efficiency loss. That's why the theorem statement is not in PV proof.
But it could potentially be the case that it just would work for any two Turing machines. Just if the translation from the Turing machine to the circuit triggered on the circuit is polynomial time.
Well, because if it's polynomial, you may not have quasi-linear efficiency because it depends on the proof. This is the EF proof length.
I see.
Yeah. So that's also why I was asking Zhenzhong the question in his talk. Okay, all right. So, yeah, so I think that's pretty much it. I mean, there are some interesting open questions. Like, for instance, we don't know whether this input length barrier is true or not. Obviously, concretely efficient I/O is a big dream that we have. This work is very theoretical. It's not concretely efficient, unfortunately. And the paper I mentioned at the beginning of the talk that led to this paper is this one. It's published in TCC 2025. There's a side story. We didn't end up rewriting this paper with this new paper. It's because in this new paper, this is also why I was asking Zhenzhong. This new paper, we still need sub-exponential security hardness. But in this paper, if it's just for this router application, we can get it with polynomial hardness. Thank you.
go directly into it now that we're into proof? Surya, you wanna set up? We have one more proof talk.
Okay,
Yes.
great. Yeah, I promised Surya I will make some time for her, so I did.
Thank you. I appreciate it.
All right.